Good evening, everyone, and welcome to Observatory Nights at the Harvard-Smithsonian Center for Astrophysics. Tonight is all about black holes. Now, for decades, black holes have captured people's imagination. They've been featured in movies, everything from the rather cheesy Disney production that was imaginatively called The Black Hole, to more recent productions like Interstellar. Black holes have been encountered by everyone from the crew of Star Trek Voyager to the Doctor of Doctor Who. And a black hole has even made an appearance in a song by the Canadian rock band Rush. Now, black holes are a paradox. I mean, a black hole itself is an object so dense that not even light can escape. But quasars that are powered by black holes are some of the brightest objects in the universe. Now, everyone knows that anything that gets too close to a black hole is just going to disappear inside and can never get out again. But Stephen Hawking has told us that black holes actually emit quantum radiation and can eventually evaporate. Here at the Center for Astrophysics, we have made a cottage industry out of studying black holes with the Chandra X-ray Observatory, which is operated from a control center right here in Cambridge, Massachusetts. Now, tonight's speaker, Paul Green, has worked at Chandra since 1996, which is 3 years before its launch. So he's been studying black holes or working on black holes for a while. Trust me, we could study black holes before Chandra, but Chandra does it way better. Paul has a bachelor's degree in physics from Oberlin College and a PhD from the University of Washington. And when he's not studying the mysteries of the cosmos, he's busy playing bass for the Wicked Pickers. So please welcome tonight's speaker, Paul Green.
Thank you, Christine. Thanks a lot. I think you only gave away the punchline to 4 or 5 of my slides, but that's okay. No, it's great. It's a pleasure to be here. It's an honor to be able to talk to so many people at once. And I feel that a big part of that honor is just actually because everyone is really into black holes, because they're just so cool. And we're going to talk about monster black holes in particular and how they get to be monsters. But I want to back up for a second and start with the really, really big picture. Okay, so a lot of you know the universe was born as we know it in a Big Bang. And we have the age since the Big Bang from many different techniques, and it's 13.7 billion years. At that time, the matter that was created in the Big Bang was 75% hydrogen and about 25% helium by mass. So those are the lightest elements in the periodic table, right? But out of those elements, out of the gas and dust that was formed in the Big Bang, stars formed, the very first stars. And what stars do, what defines a star, is nuclear fusion in the core of a star. They combine atoms and they get energy out. That's what holds the stars up and keeps them from collapsing. So the nuclear fusion of hydrogen and helium is what powered them. But that fusion itself creates new elements. So it was the first generation of stars that started to create elements like carbon, nitrogen, oxygen, all the way up the periodic table to iron. And those really massive stars then exploded as supernovae. Okay, so the first generation of stars is born, they make all these elements, and then kablooey, they blast it out into the interstellar medium and into the universe. So the picture on the left is a cutaway diagram of a star that's been cooking for a long time. It's been burning elements and making heavier and heavier elements. And each element that it makes, the heaviest ones sink towards the core. So you get this kind of onion skin effect. But once a really massive star has been around for a long time, it develops an iron core, and that's bad news. Because an iron core cannot be burnt anymore. There's no more burning you can do and still get energy. So what happens is the star will stop being able to hold itself up. It'll implode and bounce off of the iron core and turn into a supernova. So on the right, not at all to scale, is a supernova remnant. And if the original star were shown deep inside that remnant, it would be sort of like that little dot there. So the star explodes and it sends all of those elements out into outer space. So what happens then? So that material in outer space and all the gas and dust has been enriched now with heavier elements. And stars and planets form from those heavier elements, right? And then let's say on some planet or other, life evolves from this stardust, shall we say, which has been generated by this first generation of stars. And life evolves and maybe it develops intelligence. And here we are. This is us. We're kind of the intelligence of the universe, and we're all here thinking about the universe. So even though we're made up of 90% stardust ourselves, here we are looking up and wondering about the universe, trying to understand it. That's us, and I just think that's cool. So the talk, we're going to talk about the definition of black holes. We're going to talk about the smaller size black holes, stellar mass black holes, and we're going to talk about the giant ones, supermassive black holes. We'll talk about where they come from. Then we'll try to connect those two kinds of black holes, the stellar mass ones and the supermassive ones. And then I'll wrap up talking a bit about the future of black hole science. So, okay, what's a black hole? Surprisingly, even though it's so cool, a black hole is basically the simplest thing in the universe. Since everything falls into it and it's black and you can't see it and you can't measure anything inside of it, actually the only thing you can measure is its mass and maybe its spin. So that's an extremely simple object. But to be a black hole, you don't have to be incredibly massive. You just have to be incredibly dense. Even you could be a black hole. But we'll talk about how small you would have to be to become a black hole in a minute. So the deal is you would have to be so dense that even light couldn't escape your orbit. Within a certain distance from a black hole, even light can't escape. So if light can't escape from the object, well, it's black, so hence the name. Okay, the deal is that close to a black hole, the escape velocity, in other words, the speed you need to get out of its gravitational grip, is the speed of light. You have to, if you get too close, even if you travel at the speed of light, you won't be able to get away. And the speed of light, as it turns out, is the speed limit of the universe. You cannot, there is nothing you can accelerate that could go even as fast as the speed of light, let alone faster. It's the speed limit of the universe. So 186,000 miles per second, that's the speed of light. So that means nothing can get out of a black hole, not even light. So what happens in a black hole stays in a black hole. So let's talk about sizes. How big is a black hole? First, I'll point out Carl Schwarzschild, a physicist who, in about 1915, solved the analytic equations to Einstein's general relativity in a closed form and helped to make black hole science possible. So basically, we define a black hole by that radius, the radius where if you come to this particular distance, you have to have the speed of light to escape. So the distance from a black hole where the escape velocity is equal to the speed of light is called the Schwarzschild radius, after Carl Schwarzschild. And it's actually a really simple equation. I know a lot of people tense up when they see an equation, but it's not bad. Look at that. The Schwarzschild radius, r, is equal to 2g m over c squared. Well, everything there is just a constant except m, really the mass. Okay, so the radius at which you become a black hole is directly proportional to the mass. So more massive black holes have a larger Schwarzschild radius. Okay, so what is the size that the sun would need to be shrunk down to in order to become a black hole? It's 3 kilometers. So the sun would have to be only 3 kilometers across to become a black hole. I guess that's about 2 miles. And the Earth, in order to be dense enough to become a black hole, the Earth would have to be scrunched down into 1 centimeter. That's how dense a black hole is, okay? And you, a person, would have to be scrunched down to 10 to the minus 21 centimeters. And that's a ridiculously small number. That's like 100 million times smaller than the nucleus of an atom. So don't worry. I don't think you're in any danger. So the Schwarzschild radius of a black hole is called the event horizon, which I think is a cool name because it's the horizon past which, going in towards a black hole, you can't see anything. You can't know about any events. It's the horizon of events. So nothing within the event horizon can escape the black hole. A lot of people are worried about black holes. They feel like if there's black holes in the galaxy, aren't we in trouble? Aren't they going to suck us in eventually? And that's not really an issue because the strange gravitational effects of a black hole only happen when you're close to that event horizon, when you're very close to it. But a few times that distance away, and it's just another gravitational object. It's just another mass. So black holes don't suck things in any more than anything else would. It's just that you can get so close to that mass that you might be in danger then. For instance, if the sun were replaced by a black hole right now in the dark at night here, we pretty much wouldn't know. If the sun suddenly became a black hole, the Earth's orbit wouldn't change, right? Because the Earth's orbit around the sun is determined by the mass of the Earth and the mass of the sun and the distance between them. That's all. So if the sun suddenly became a black hole, Earth would still go on its merry way. It's just that in the morning, it might be kind of weird. You'd think like, wait, is it daylight savings time or is it standard time? You know, because the sun wouldn't come up. But no worries. That's not going to happen. So anyway, if black holes are invisible, how do we know they exist? The thing is that black holes with their intense gravity, they can affect the material around them in really strange ways. Okay, so a black hole, if it's in an environment with stars and gas and dust around it, sort of like happens pretty often in the universe, it will pull that stuff in. And as the gas and the dust funnels down towards this intense gravity, it heats up because of just turbulence and friction. And it heats up and starts to spin around the black hole as it's getting pulled in, almost like going down a drain or something. And when that happens, that's called an accretion disk, because it's accreting material and it spins into a disk, and it heats up so hot that it becomes extremely high luminosity. It has really weird colors too. It doesn't look like a star. And also, since it's such a small area down close to the black hole, it can have really rapid variability, much more rapid even than a star might have, because it's such a small area. So the accretion disk, you might want to remember that term. That's the stuff that's getting pulled in. Also, we can see the effect of black holes on stars. Sometimes you can see stars actually going around a black hole, and we'll talk about that. And spectacularly, last year, for the first time in human history, gravitational waves were detected, which are direct evidence of black holes that were predicted back in about 1916 by Einstein. And here is a sort of a record of this gravitational wave event. Some of you probably saw this in the news. There's a laser interferometric gravitational observatory, LIGO, that made this detection after millions of dollars spent on the detectors and having the detectors in Hanford, Washington, and another one in Livingston, Louisiana, to make sure that this disturbance that they registered wasn't just a truck going by. They had to have the two stations widely spread apart. And this shaking of space is literally what they detected. And you can see the shaking in Hanford, Washington on the upper left and Livingston, Louisiana on the upper right. That's the data. The general relativistic theoretical model is the second level of plots, and you can see how nicely the model fits the data. It looks almost just like the real data on top. And the whole event lasted less than a second. And you can see what this is a plot on the lower part of what it sounded like. Basically, it made a sort of a whoosh, chirp sound, and they recorded it and fit it with the model, and it was a spectacular coup for science in this millennium. So this now is a simulation of what that black hole merger might have looked like if you could have seen it from space. And the intense gravity of the black holes actually bends the light from behind the black holes. So the stars that are behind these black holes actually look kind of warped, and space looks warped around it because gravity actually bends light. That's what Einstein's general relativity says, is that gravity actually is just the curvature of space. Mass curves space. Oops, that was supposed to play. Here we go. Now that black holes are getting close together, and they're going to merge into one even more massive black hole. And that'll happen. This is about, there you go. This whole video takes about 15 times as long as the actual event did. So, what are some other ways we knew that black holes existed? Because before last year, before the first detection of gravitational waves, we knew they existed too. The first black hole to be discovered definitively was called Cygnus X1. X1, that's because it was the first X-ray emitting black hole discovered. And Cygnus because that's the constellation in the sky where it was found. There are about 20 or so such black holes known now in our galaxy, in the Milky Way Galaxy, in our cosmic neighborhood, okay? But when you do the math, we suspect that there's probably about 100 million black holes in the Milky Way. It's just that only some of them are have these luminous accretion disks right now that make us able to see them. So, in 1964, a very crude precursor to today's sophisticated X-ray telescopes was launched. It was basically a bunch of Geiger counters were launched into space, and they discovered that there were X-rays coming not just from the sun, but from other celestial sources as well. That led to a proposal for a satellite launched out of Kenya called Uhuru, which is Swahili for freedom. And it was developed here in Cambridge, Mass, at a place called American Science and Engineering by Riccardo Giacconi, who's now a Nobel Prize laureate, and by a number of scientists that still work here at the CFA on the Chandra X-ray telescope. So Uhuru was launched in 1972, and it promptly found about 400 celestial X-ray sources across the sky. Cygnus X1 did not originally have a big red box around it. I actually put that there. But here's what it looks like in the optical. It's a small kind of fairly anonymous looking star in visual light in an optical picture. But in the X-rays, it would be the brightest thing in this whole picture. It just blows everything away in the X-rays. So that's why it's important to use different wavelengths and different energies when you're looking at the sky. So this is an artist's depiction. I wish we had a telescope that could see it this clearly. But this is a collaboration between an artist and a scientist. to describe Cygnus X1. So here's the accretion disk. You see the, funneling down matter onto the black hole. The black hole also emits jets sometimes in certain phases. This black hole is 15 times more massive than the sun. It's about 6,000 light years away. And in fact, it's 300,000 times more luminous than our sun is. So it's very small, but it's extremely luminous. That's what black holes can do. In fact, the light travel size, as they say, is 140 times smaller than the size of the sun. What's the light travel size? That's just how long it would take light to get across it. So if it varies up and down and gets brighter and fainter, kind of all at once, you know that the rate at which it varies tells you how quickly the whole region is connected by light. The whole region knows about other parts of the region. So the quicker something varies, the smaller it must be. All right, wait a second. What's all this luminosity business? No light escapes from a black hole, right? Well, it does, right? Because it's not from the black hole that the light is coming. It's from the accretion disk and the other regions around it. It's the material that's falling in towards the black hole. It hasn't yet fallen in. So I'll tell you about one other really cool stellar mass black hole in the galaxy. It's called V404 Sig. It has a nickname of a micro quasar, and I'll be telling you about quasars more in a minute. But it again has these wild outbursts and gets extremely bright. But this one was quiet for 25 years up until last year, and then it suddenly flared up. This black hole weighs about 12 times the mass of the sun, and it's about 8,000 light years from here. So the flare that we saw last year happened about 8,000 years ago. And here's an artist's depiction. So there's a sort of a normal star next to it, but it's unlucky enough to be near this black hole that's pulling material off of that star onto an accretion disk, which glows extremely brightly and shoots out jets of material. But then sometimes the accretion stream just stops and it goes quiet for a while. So this is a common configuration of a black hole X-ray binary in our galaxy. So where do black holes come from, these kind of stellar mass black holes? Well, they come from stars. Stars start, if you look all the way on the left, as these big clouds of gas and dust, these stellar nebulae. They collapse from their own gravity and become normal stars. That's kind of like the sun up there, that yellow thing, average star, right? The sun has been around about 5 billion years. In about another 5 billion years, it's going to start to die, and it'll become a red giant. And then it'll blow off its outer layers and become what they call a planetary nebula. Has nothing to do with planets. It's just a historical name. And then only the core will be left, which is pretty much just carbon and oxygen left over from the nuclear fusion, and it'll be a white dwarf. That's what the sun will do. But really massive stars, like 8 times the mass of the sun or so, follow the track along the bottom. Okay, a massive star becomes a red supergiant, and then after it's started to burn, to try to burn iron in its core, as I was talking about at the beginning, that just fails, and it'll explode as a supernova. And then the core of the supernova could go two ways. It could end up as a neutron star, which is literally made up almost entirely of just neutrons, like the nucleus of an atom. Or if it's really heavy, over 3 times the mass of the sun or so, it'll become a black hole. So that's where black holes come from. All right, now what about supermassive black holes? We've been talking about black holes that weigh sort of 3 times the mass of the sun, or 10 times, or a dozen times the mass of the sun. And those stellar mass black holes are kind of peppered throughout our galaxy, and presumably other galaxies too. But we also know that there are supermassive black holes. In fact, the centers of most galaxies, like our own, contain supermassive black holes. Okay, just for a second, what's a galaxy? A galaxy is, in our case anyway, it's a big pancake-shaped thing that has billions of stars in it. Sometimes galaxies are shaped like footballs, but they're basically far apart from each other, and each galaxy contains billions of stars. Okay, and within pretty much every self-respecting galaxy, there's a supermassive black hole in the core. We don't know exactly why or how, but that is a known fact. And those supermassive black holes range from a few million to a few billion times the mass of the sun. Okay, and a billion is a big number. I once calculated that if all you did all day long, 40 hours a week for your job, was just to count 1, 2, 3, 4, 5, 6, 7 as fast as you could, it would take you more than a lifetime to count to a billion. It's a big number. Okay, so there is a supermassive black hole, and excuse me for using acronyms. Astronomers love acronyms. A supermassive black hole, an SMBH. There's a supermassive black hole in our own Milky Way, and it's called fondly Sagittarius A star, because it was first discovered as a very bright radio source in the constellation Sagittarius, which is towards the center of our galaxy. Sagittarius A star is invisible in optical light. You cannot see it, even with a powerful telescope. That's because it's in the center of our galaxy, and there's a lot of junk, gas and dust and stars between here and there, and the light just doesn't get through. But in the infrared, you can see it. In the radio, you can see it. And in the X-rays, you can see it. It's 26,000 light years from here. And in the infrared, scientists, I think it was at UCLA, were able to see stars that were orbiting around the supermassive black hole in our galaxy. And by tracking those stars and taking images repeatedly, watching them move, they were able to track the orbits and therefore determine the mass of this supermassive black hole. And those stars are moving at up to 2 million miles per hour around Sagittarius A star. And it turns out that the mass of it is about 4 million solar masses. And there's even a little movie based on those observations that spans 10 years. They took repeated images in the infrared of these stars moving in the center of our galaxy over 10 years. Now let's zoom in and we'll look at the one star that was really the most helpful. They called it S2, with this yellow track and the data points there as it was seen moving in the vicinity of that black hole. Okay, so we know there's a supermassive black hole in the center of our Milky Way. We actually knew that there were other black holes in other galaxies before we even knew about the one in our galaxy, and that's because of quasars. People sometimes get the word quasar and pulsar mixed up. A pulsar is a neutron star that's spinning really fast in our galaxy. A quasar is actually a supermassive black hole in the core of a galaxy that's not just sitting there, it's actively accreting, it's pulling in material. And so galaxies with active supermassive black holes, well, they're called active galaxies. They're also called quasars when they get super bright. In fact, even though this supermassive black hole is comparatively tiny, it's thousands or 10,000 times smaller than the galaxy, it's 1,000 times brighter than the entire galaxy. So actually, quasars are some of the brightest objects in the universe, as Christine mentioned, but they're so far away in the nuclei, in the cores of distant galaxies, that you can't see them with the naked eye. Okay, they're some of the most luminous things in the universe, but they're so far away that they look really dim. But we know they exist from telescopes. Even a typical average telescope, you can find quasars to look at, and I've done that many, many times. I love quasars. Clearly, I don't know much about Photoshop. So there are supermassive black holes that inhabit the cores of all galaxies. So this is an artist's impression, sort of zooming in on the nucleus of this galaxy of what a black hole might look like. You see the accretion disk is glowing very brightly in the middle of that inset. And then around it, there's a sort of a torus, a donut-shaped cloud of gas and dust. And this is how we really think quasars look if we could zoom in like that in real life. The reason they're called quasars comes from the word quasi-stellar, because they're so compact and so bright that they look like stars. They really do. On the left here you see a picture of the first quasar ever discovered, which is called 3C273 because it's the 273rd radio source in the 3rd Cambridge catalog of radio sources. And look at that. It looks just like a star, right? It took the Hubble Space Telescope to use a coronagraph, which is a special trick way of blocking the bright part of the image, blocking the core of the image, to enable us to actually see the galaxy that surrounds that supermassive black hole. Okay? So quasars are extremely luminous. They're very compact. And they even shoot out jets, just sort of as we saw in some of those artist depictions. And you can just see this jet that's shooting out from 3C273. This thing is about, I think, as long as the Milky Way itself. Enormous jets. They're extremely variable also. This is what we call a light curve. It's just the brightness of 3C273 from 1890 to 1960. And the light curve shows strong variability. It doesn't just stay constant like a star does. This is something that all supermassive black holes seem to do. The other way that supermassive black holes are strange is that they have an extremely broadband spectrum. Okay, a normal galaxy, this curve shown at the bottom, emits mostly in the visible, a little bit in the infrared, and that's because a normal galaxy is composed of billions of stars, so it's just the sum of all the starlight, and it's normal kind of starlight. But supermassive black holes in active galaxies span a much wider range of the electromagnetic spectrum, all the way from X-rays at the high energy end through the visible, the infrared, the radio, and beyond. So what we call the spectral energy distribution is really wide. I want to take a second to give you astronomy 101 description of spectroscopy, astronomical spectra. What do we use spectra for? Okay, you can take pictures, you can take images of an object, and we've seen that. But if you can get even more information if you take that image and you run it through a prism and spread the light out like a rainbow. On the left, you can see spectra that are spread out like a rainbow. And you can also see, though, that some of these have bright lines in them. And different elements give off different lines, like hydrogen at the top. You can see one bright line there. And anytime you see hydrogen emission anywhere in the universe, it's going to give off that same line. You can recognize hydrogen anywhere in the universe. And helium has a different set of lines. So you can, when you spread the light out in a spectrum, you can see this broad spectral energy distribution, which we call the continuum, but you can also learn something about the atoms that are there. So this is what a spectrum of a galaxy looks like. It's got a continuum, which is basically summing up billions of stars. But it's also got these strong emission lines from certain particular atoms. This is from hydrogen here. Oh, right. So I wanted to tell you also about the Doppler effect, which you may know about. Unfortunately, there's a slight technical glitch here so that the sound isn't going to work. So I'm going to try to provide the sound. I think everybody knows what the Doppler effect is like. Oh, wait, you can hear it from my laptop. Guy's playing a trumpet in his car. To him, it's just one frequency. He's playing one note. But then if he drives by somebody, the Doppler effect scrunches up the waves coming from that trumpet. So it sounds a higher frequency. And then when he goes by, the waves are getting stretched out by his velocity, so the frequency goes lower. Okay, that's the Doppler effect that we're all familiar with in terms of sound, but it's the same thing with light. It does the exact same thing. So if an object is moving towards you, the waves, as you see on the left, the waves get scrunched up and they actually become higher frequency, which means the light becomes bluer. If the object is moving away from you, the waves get stretched out. It seems to be a lower frequency, longer wavelength, and the light looks redder. That's a redshift. Okay, that's the Doppler effect, and it's very useful in astronomy. But it also tells us a lot about quasars, okay, because remember that in the accretion disk, there's gas that's moving around the supermassive black hole very rapidly. So some of it is coming towards you and getting blue shifted. Some of it's moving away from you and getting red shifted. So the light is getting spread out. Some of it's blue shifted, some of it's red shifted. And by adding up all of that light, which we only see coming from one point all mixed together, you get a much broader line, as you see on the left there in this cartoon. So that's what helps us discover quasars as looking different in spectroscopy from galaxies. On the left, there's a galaxy with those skinny, narrow emission lines corresponding to hydrogen, nitrogen, oxygen, etc. On the right is what a spectrum of a quasar looks like. Wow. For me, that looks totally different. Maybe for some people, it's just a bunch of squiggly lines. But for me, I see lots more light at shorter wavelengths here, so it's very blue. And I also see that these emission lines are extremely broad. That's the Doppler broadening caused by the supermassive black hole. So that's how we know this is a quasar. So where did these supermassive black holes come from? When did the first one form? Well, the weird thing is that we can see quasars really far out in space, right? Because they're so super bright. In fact, quasars are some of the most distant things that we've been able to see for a long time. The redshift record is 7 for a quasar, which basically corresponds to how much its light has been stretched by the expansion of the universe since the Big Bang, and that tells us how far away it is. The redshift record of 7 corresponds to about 13 billion years ago. So almost all the way back to the Big Bang, there were these supermassive black holes. That's only about 500 million years after the Big Bang. That's peanuts. How do you get a billion solar mass black hole that quickly in the universe? And the answer is, we have no clue. There are some theories. One of them is that back when the universe was all hydrogen and helium and didn't have all these metals and heavy elements in it, it was easier to form really, really huge stars. Primordial massive stars were easier to form. So that's one possibility. Other people think that it might be these star clusters, very, very dense star clusters that were kind of in the nuclei in the cores of early galaxies. And through various processes, a lot of stars combined and black holes combined to make really large ones. But we just don't know. So even if you have a seed black hole from one of those processes, so how does it grow into a really supermassive black hole? A number of different ways, right? It inhales gas and dust that gets too close to it. It eats stars that get too close to it. It might merge with other smaller black holes, or it might merge with a same size black hole. Supermassive black holes merging together. So these are all possibilities. And here what I have is a numerical simulation done on a computer of what it would look like if a star gets too close to a black hole. This is called a tidal disruption event, a TDE. I told you we love acronyms. A tidal disruption event happens when a star gets so close to a black hole that it gets shredded. The tidal force means the gravity on the close side is so much stronger than the gravity on the far side that it actually gets pulled apart. The star gets pulled apart and shredded, and it goes into an accretion disk and then lights up the supermassive black hole. Okay, so here's what the computer simulation shows, which matches our observations pretty nicely. On the left, we're looking at the black hole and the accretion disk from the top, and on the right, it's just a side view. So along comes this hapless star, gets shredded, circles around the black hole, gets shredded some more, turns into an accretion disk, starts to glow very brightly. And then it would actually fade relatively soon after that. So that's what's called a tidal disruption event of a star that gets too close to a black hole. Okay, but black holes can also grow by merging together. When galaxies merge together, supermassive black holes merge together too. This is a paper I wrote a number of years ago about two supermassive black holes that appear to exist within the same galaxy. And it's certain that this galaxy was the merger of two large galaxies very recently. And you can see the sort of tidal tails that sweep out from the core are still there. And this is the spectrum of the two quasars that are inside this galaxy. You see the broad emission lines there. And my theoretical friend, T.J. Cox, on a supercomputer, created this video to explain what happened. So here's one galaxy just minding its own business. And then about 500 million years later, this other galaxy comes by in orbit, and that passage strips out streamers of stars from these galaxies. Galaxy number 2 is going to come back for a second pass about 1 billion years later. Not in real time, it'll happen in a few seconds. Here it comes, kablam, and there you go. And that's the simulation, which you can compare to the actual image. Pretty cool. Oops. Okay. Yeah. Love that stuff. Any kind of train wreck like that is fun. Okay, so what happens is these galaxies smash together and their black holes combine and merge. And interestingly, if you look at the sizes of supermassive black holes and you compare it to the masses of the galaxies that they inhabit, there's a very strong correlation. That's a correlation shown there. On the vertical axis is the black hole mass, and on the horizontal axis is basically the mass of the galaxy as we measure from its stellar velocity dispersion. Okay? Sounds very fancy. But to have such a tight correlation, this is good for astronomy. I don't know, maybe in some other fields this would not look impressive, but to an astronomer, that's a good correlation. It's tight. All these objects pretty much fall along this line. And what's so weird about that is that a galaxy, again, is 10,000 times smaller than the whole the supermassive black hole is 10,000 times smaller than the whole galaxy. So how could it possibly affect an entire galaxy? Again, we don't know. But there's a lot of theories about it, and there's some very intriguing observations too. The process has been given the name feedback. Okay, here is a movie of galaxy growth. Okay, in the universe, galaxies grow by the collapsing together of smaller galaxies and of gas and dust, and that forms all the galaxies we know of, and those galaxies form in these long chains they call filaments. So this is a massive supercomputer simulation, basically of the formation of the universe. So this is a large volume of space containing many thousands or millions of galaxies. The galaxies form at these sort of bright spots along these filaments. We're starting back close to the Big Bang and then running time forwards, getting close to the current epoch. And now this is a different sort of view that shows you where the black holes are forming and where the supermassive black holes are forming in these galaxies. They blow out gas and dust, and they slow down the formation of galaxies. And that is what they call feedback, and that's what creates that tight correlation. It prevents galaxies from getting really large. So how does black hole feedback actually work in galaxies? And we have another video. Here's a large galaxy, and deep down inside of it is a black hole and its accretion disk and that donut sort of gas and dust around it. When the accretion really funnels down toward the black hole, that accretion disk gets very bright and starts to blow out a wind because of that intense luminosity. And that creates a shock wave that then travels outward from the supermassive black hole into the galaxy. And in the galaxy, there are these star-forming regions where cool gas and dust is slowly condensing to form stars. But when this shock wave goes out, it disrupts all that. It disrupts star formation by shocking all of those molecules and that dust and preventing the formation of stars. And that's how supermassive black holes affect galaxies. So look, we've talked about stellar mass black holes. We've talked about supermassive black holes. Are they connected? Well, the math says that they are. And there's also observations that say that they are. You can put them on this particular plot that correlates basically radio power and X-ray power from these black holes. And down at the bottom left are the stellar mass black holes that exist in our galaxy that are anywhere from 3 to 10 times the mass of the sun. And up here are the supermassive black holes that are 1 billion times heavier. So this physics connects these things. There's two remarkable features. One is that there's nothing really in the middle of this plot, which is kind of embarrassing. We don't know where those are. I'll talk about that in a second. But the physics also tells us that everything should scale up. The physics scales up by a factor of 1 billion, and it should scale with mass. And so if a stellar mass black hole is variable on timescales like we see, timescales of an hour or so, then a supermassive black hole should take 10,000 years or more to make a change like that. So we shouldn't see quasars changing, really, very much. They should never basically shut off, for instance, the way that a stellar mass black hole does. But lo and behold, in the last couple of years, my team and some other folks as well have discovered these weird things. We call them changing look quasars, and they've actually turned off. At the top spectrum is a normal quasar spectrum. And then a few years later, a spectrum of the same object was taken. The blue light on the left, The strength of that blue light diminished by a large factor. These broad emission lines went completely away. What the heck? This was a surprise. Large luminosity changes like that should take thousands of years, and instead it took a few years. So how could that happen? Well, first we thought maybe it got really cloudy down there. Maybe there's a lot of junk that just got in the way, which is a possibility, but that would take thousands of years too. You can't cover up a supermassive black hole overnight. Okay, so it's not dust, it's not clouds. Maybe it was a supernova or a tidal disruption event. Well, that doesn't work either because those don't last very long, whereas these quasars had been going, we know, for decades or more, much longer than a supernova. So we think it was just a change in the accretion rate. For some reason, the accretion disk, just the inner parts of it evaporated, or there's sort of braids in it or rings in it or something. But these changing look quasars really challenge what we know about accretion theory, about accretion disks. But the one other cool thing about them is that they actually enable you to take a look at the galaxy, which is otherwise just completely blinded by the quasar. So we can study the host galaxies of these quasars by using these objects that turn on and off unexpectedly. I'm really a little over time, but people love movies, don't they? Oops. So this is a movie of the changing look quasar and how it might look in the accretion. So the accretion is happening strongly here, and that's what the spectrum looks like. But then if a gap opens up in the accretion disk and it stops accreting, all that light goes away. And the emission drops. Here's another idea of what it might look like. Whoop, the light shut off, and so the spectrum changes. And a final artist depiction of it. So all this light gets beamed out from the quasar, right, as it's active, and it lights up everything around it. Once the quasar shuts off, the light that's still streaming outward would continue to illuminate things that are far away, but eventually even those would shut off. So by studying how this changes with time, we can learn about the physics of these supermassive black holes in the changing look quasars. Okay, the missing link, as I showed you in that plot that connected the stellar mass black holes to the supermassive black holes, there was nothing in the middle. Where are these things? Where are the teenage black holes? Okay, there are some of them. We know about some of them. They're really rare, really hard to find. They're called ultraluminous X-ray binaries, or intermediate mass black holes. And we don't know exactly how they form, but it's probably a similar way to the way the seed black holes formed back in the early times of the universe. Here's an example, one teenage black hole in the outskirts of the galaxy where that black circle shows where this X-ray, ultraluminous X-ray binary is. It weighs about 10,000 times what the sun weighs. It flares up with these extraordinary X-ray light curves. You see the flares happening there in the lower left. And we don't know how it formed. It could be that it was actually the core of a small, very small galaxy that fell into this larger galaxy. And the stars got stripped, leaving only the black hole there. So what's going to happen in the future with black hole science? A lot. As you've seen, there's a lot of things we don't know. There's a lot of interesting things yet to discover, and maybe some of you in this room will help. Just down the street is a new initiative called the Black Hole Initiative, where astronomers, physicists, and philosophers are getting together to talk about black holes and to try to understand them. There's some new telescopes being built. Some of them are already underway right now. For instance, the Event Horizon Telescope. And there are scientists here that are working actively on that. it has a much more unwieldy name, the Global Submillimeter Wavelength Very Long Baseline Interferometry Array. It's composed of a large number of telescopes around the globe, and it's already starting to actually get images, not just spectra, but images of Sagittarius A star in our galaxy and the supermassive black hole in the nearest active galaxy called M87. There's an initiative by the European Space Agency called LISA, the Laser Interferometry Space Antenna, which will very sensitively detect gravitational waves. And there is the X-ray Surveyor, which has just recently, I heard today, been renamed LINX, which is a project that we are going to propose to NASA and to the government and to hope that we can build this X-ray telescope in space. This is what X-ray Surveyor might look like. It'll be an incredibly powerful, sensitive, and precise space telescope to measure X-rays, a successor to the Chandra Observatory that's still working beautifully right now over our heads somewhere. But it'll be 50 times more sensitive, and also have a larger field of view, and it could even detect these seed black holes throughout the observable universe, all the way back towards the Big Bang. So thank you very much for your attention.
All right, I know there's going to be some questions after this, so why don't we start over here?
It takes infinitely long in our time frame for an object to fall into a black hole. So how come you're able to see two black holes merge so quickly?
The two black holes merged within a second or so, right? And they shook space when they did that. That curvature shook space, and the ripples went outward. So.
But shouldn't that only occur in the infinite future?
No, that's a disturbance that propagates at the speed of light across the universe.
I get what he's asking, and I'm not quite clear on it either. It gets into that weird general relativity stuff. Over here.
How were the heavier elements created when the stars explode? You stop it at iron.
Right. The elements heavier than iron can be created in the supernova explosion. So they're not created in bulk in the normal burning that takes place in a star. But heavier elements can be created in the explosion itself.
Young lady, yes.
Okay, so you were talking about changing little quasars, and you said that you've seen them shut off.
Yeah.
Have you ever seen one like shut off and then turn back on again?
Great question. Yes. There's a couple that we've seen do both. And we're looking for more of those. It turns out that it's been a lot easier to find the ones that shut off because there's a lot of spectra of quasars because they're so bright. We know about a lot of them. But quasars are a pretty rare phenomenon. They only happen in maybe 1 out of 1,000 galaxies. So we haven't been monitoring all of those galaxies. It's been easier to follow the quasars. But we now are starting a dedicated program to actually look for galaxies that get brighter instead of just quasars that turn on. We're hoping to see several go in both directions also, so we can start to understand what those time frames are. Do they turn on and off quickly, or does it last for a long time? That kind of thing.
Questions upstairs? Oh, you look like you might be raising your hand. No.
Well, I do have one that I've been. What is the longest supermassive black hole we have found to date, and could we find one even bigger than that?
Ooh, what's the biggest black hole we found?
I think the biggest one is probably about 10 billion. Solar mass is about 10 billion times the mass of the sun. And if we keep looking, I'm sure we'll find something just a little bigger. I wonder if there is some kind of limit. Like,
Yeah,
could you ever have something that's 100 billion times the mass of the sun?
a trillion?
Yeah, I don't actually know. But if we wait around a few more billion years, that'll give those supermassive black holes time to grow even more.
Well, that shouldn't take too long.
Yeah.
Yes, sir.
Is it conceivable that these large-scale merger events between black holes would actually affect us? Like all of a sudden, without knowing, our star would comes to orbit.
The answer is basically no, because those mergers of supermassive black holes happen so far away from here. And the strength of gravity decreases with the distance squared. So if you're a long way away from something, even if it's really massive or really just really disruptive gravitational event, if you're far away from it, you're not going to even notice.
Yes, in the pleasure.
When two black holes merge and you have this disturbance in space and the ripples go out, if you're close to that area, does the matter in that space get torn apart, or does it just pass through the matter? I mean, you have things within the space, so what happens to those things? What would happen to me, for instance, if I was near that? Would the ripple just go through my body?
I think essentially, I mean, if you're extremely close to these massive black holes when they merge, you'd be in trouble probably for other reasons. But if the gravitational wave passes through you, you know, space itself is going, ooh, right?
So, which means the matter is also doing
the matter is also doing that, but I think if you were close enough to notice, you would already be in big trouble. For instance, I mean, we detected those that gravitational wave that passed through Earth after this event, and there's now been two that have been detected. And the detectors themselves are exquisitely sensitive interferometric lasers, right? But they're basically measuring a distance change between them. So it's space itself that's oscillating, and that's what they measure. But it was a tiny, tiny effect. That's why it was so expensive.
Yeah, the engine.
Is there a maximum amount of light that can be sucked in by a black hole?
No, you can shine any kind of spotlight on a black hole, and all that light will just go to waste. It'll just be gone forever.
Back here.
You mentioned some things about acronyms. I've also heard machos and wimps. What do those mean?
Machos and wimps. Machos and wimps are candidates for the dark matter, and those stand for weakly interacting massive particles. For wimps, this is not at all my area of expertise, and machos are massive compact halo objects, I think. So they could be lots of little black holes swarming around our galaxy, or maybe magnetic monopoles or some other exotic objects that make up the dark matter in our universe, which actually composes most of the matter in our universe.
Could they be black holes?
I believe the massive compact halo objects could be black holes, but not the normal black holes that you create at the end of stellar evolution. Some other kind.
Back here, yes.
If we're looking at a quasar edge on, we see nice widening of the spectral lines. If I look at the same quasar down the axis, the spinning axis, I'm not going to see that. What if this disk, this galactic disk, is tumbling? So it goes on and off and on and off. The lines increase and decrease and narrow and widen as it tumbles.
Wow, interesting question. Well, first off, these accretion disks are vast, and they have, I don't know, they have many, many solar masses worth of material in them, and they're spinning. And it would take a tremendous amount of torque to change the axis of rotation, right? If you've seen these experiments, you spin a bicycle wheel that you're holding and then you try to turn it, that takes a lot of torque. Now, jack that up by thousands of times the mass of the sun, it ain't going to happen. So the accretion disks don't wobble or spin, really. I mean, they just spin around their axis of rotation. Interestingly, if you look at those things from the side, you usually don't even see the broad lines because they're obscured by this donut-shaped clouds of gas and dust that also funnel in. So the stuff that's funneling in to the black hole, when it gets close, it gets heated up and becomes see-through or even emits light. But the stuff that's farther out is gas and dust, and it obscures your line of sight from the side. So you can't actually see quasars from the side. The ones that we see are usually more or less pole on, but there's still enough chaotic velocity around the black hole to broaden the lines. Sorry, that was a little verbose.
All right, we want to get people up to look through telescopes, so one last really good question. You pick.
Ooh. Yeah.
It's a little bit different, but I was wondering if you can tell us a little bit about what models exist for wormholes, and if there's any models that connect that to your model.
Oh, I was afraid somebody was going to ask. Next question. Yeah, no, this is not my area of specialty. I don't know that much about wormholes. Wormholes, I believe, are theoretically possible. It's theoretically possible that if you go into a black hole and you were able to survive, you might go through to another universe or something. That's the extent of my knowledge. So I urge you to read about wormholes and tell me about it. I know there are experts out there like Kip Thorne and some other folks, but that's beyond me. I don't do that kind of math.
All right, let's thank our speaker again.